Hi everyone. Can you guys hear me? I hope you guys are well and ready to get started on working through physics. Just so I can get a feel of where we're at with the content, can you rate work energy and power out of 10? Let's see. We have a few attendees. How are you feeling about this topic, guys? Out of 10, where would you rate it? Okay. Some people are answering. I see 8, which is very encouraging to see. 9, which is quite good. Yeah, without further ado, let's jump into it. My name is Muranga Dao. I am pleased to be helping you guys with work, energy, and power today. Let's get ready. I hope you guys have your writing instruments, your calculators, and everything else that you need ready so we can get started. I'm going to share my screen and we can just get in from there. Okay, I take it that everybody's able to see my screen. Let's jump straight into it, guys. We are doing work, energy, and power today. This is part of our term 2 revision series. And obviously, work, energy, and power falls under physical sciences, paper 1. Let's get into it. Our topics for today are work, work energy theorem, and power. We're also going to learn and practice on how to calculate the net work, as well as all other associated variables. Let's get started with the work. Work is defined as a force acting over displacement, and it's measured in joules, with the symbol and the units given over there. Well, the symbol isn't given, but the units, it's measured in joules. I like to think of work as the amount of energy, either positive or negative, required for an action. In our case, it's applying a force over a distance. So whenever you have a force acting over a distance, just know it's work. Cool. Let's carry onwards. Let's get into the equation, guys. So we have work, the symbol W, is equals to F multiplied by delta X, our displacement, over which the force is acting, multiplied by cos theta, which is the angle at which our force is applied onto our object. Do not confuse this with the angle of inclination. Theta is in reference to I'd say the axis of displacement. Let me perhaps draw what exactly I mean by that. So look at the box over there. We have the force being applied at that angle over here. In this case, this is 30 degrees. So you know that when filling in the formula, work is equals to the force multiplied by delta x times cos theta, you substitute 30 degrees in place of theta. Provided here is an example whereby a learner pushes a 20-kilogram box with a force of 50 newtons at an angle of 30 degrees above the horizontal, moving it 4 meters across a classroom floor. Calculate the work done by the learner, and it's as simple as plugging the values into the formula. Typically for questions like these, we have a 3-mark allocation, 1 mark for the formula, 1 mark for the substitution, 1 mark for the final answer. So a question like this would have a 3-mark allocation. Cool. Let's carry onwards. Let's look at the types of work. Like I mentioned previously, we have negative and positive work. Positive work happens whereby energy is transferred to the object by a force. For example, let's reference our previous example over there with the learner pushing a 20-kilogram box. The learner is transferring energy to the box, the object on which the force is acting on. And so our work there would be positive. Okay? And then we look at negative work. It's defined as, or essentially, negative work happens when energy is transferred from an object by a force. An example I could give is friction. Friction is negative because it takes energy away from the system. We lose energy in the form of heat. Cool. If you guys have any questions, please do drop them in the chat or Q&A function. I'll make every effort to check your questions out and make sure that I answer them. Right. Over here, we have some visual examples of what exactly is happening. We have over there, if you look at the first example right here, we have our force acting towards the right, our displacement going towards the right, and so our work that happens, which is 50 joules, would be positive, right? I perhaps missed that well, I didn't miss anything. All the information is necessary, is present here. And let's continue onwards. If we jump to the second example, whereby our force is applied at an angle of 30 degrees, we see that we put the 30 in the brackets over there, and we end up with a positive work. We are adding energy to the system. Cool. If we go to example 3 over here, our displacement, delta x, is to the right, 5 meters. Our force that's being applied is F, which is 10 newtons upwards. But we don't have work happening. The reason as to why we don't have work is because in order for work to happen, our force has to be applied in the direction of our displacement or along the axis of displacement. In this case, we have a vertical force that is perpendicular to our displacement, so there's no work happening. For work to happen, it has to be along our axis of displacement. Cool. And then if you go to example 4 over here, our force is to the left, our displacement is to the right, and so we end up with our work being negative 50 joules. We're taking right as positive, as well as up as positive. Can you hear me a bit better now? Cool. So yeah, typically you work with up as positive, right as positive, down as negative, and left as negative. All right, let's carry onwards. Let's get started with the quiz to make sure you guys are actually paying attention and you guys are attentive to this lesson. We have a question that reads as follows. A block moves along a rough horizontal surface while a horizontal force F of magnitude 80 newtons and a constant kinetic frictional force of magnitude 6 newtons act on it. Which of the following combinations of acceleration and network done on the block is correct? Do you guys think it's option A, option B, option C, or option D? Let's see what your guys' answers are. Please do drop them in the chat. What do you guys think the answer to this question in particular is? We have option A saying that it's constant acceleration, increasing network. Option B says increasing acceleration, increasing network. Option C is increasing acceleration, constant network. And option D is it should be constant acceleration, constant network. Let me fix that now. Cool. What do you guys think the answer for this quiz is? Okay, some answers rolling in. Somebody answered A. Do we agree with that answer? All right, so yeah, the correct answer for this one is indeed option A. And let's explore why exactly that is. So we know that the net force acting on an object is directly proportionate to the acceleration. This is from Newton's second law, if I'm correct, whereby we have F net is equals to MA. F net being directly proportional to A. In our case, we can calculate our net force easily. We're just going to take the sum of the forces along the x-axis. We'll then have 18 minus 6 newtons as our net force. And this gives us a value of 12 newtons. 12 newtons is a constant value. We have a constant net force over here. Therefore, our acceleration is constant as well. We don't have a variable acceleration in this case because you see our F net is always going to be 12 newtons. Cool. Now, let's get into what exactly happens to the net work that happens over here. So for the net work, we should be recalling the following formula, or just the work formula in general. We have the work is equals to force times delta x times cos of theta. In this case, we're dealing with the net work, so I can use the net force. I then have net work is equals to net force multiplied by our displacement multiplied by cos of theta. Cool. Based off what I've written over here, I can see that my net work is directly proportionate to my displacement. And now, because we know that our box is traveling, are you guys able to hear me? Maybe a bit better? Okay, I'll continue onwards. I'll just try to project my voice. So because we know that our net work is directly proportionate to our displacement, and we know that our box is traveling, in this scenario in particular, our box is continuously traveling. That means our displacement is continuously increasing because our box is traveling. And so we know that if our net work is directly proportionate to our displacement, if this one increases, this one over here also has to increase. And that's why the answer to this quiz is A. All right, are we all good with that? Right, let's carry onwards. Now let's get started on the work energy theorem. The work energy theorem states that the net work done on an object equals to the change in its kinetic energy. Let's explore what this definition means. But before we do that, we have to make note of a few other concepts. So right now we're looking at the conservation of mechanical energy, and what this states is that the total mechanical energy, which is the sum of the gravitational potential energy and the kinetic energy, in an isolated system remains constant. A system is isolated when the net external forces acting on it, excluding gravitational force, is 0. Cool. We typically can identify an isolated system from a non-isolated system depending on the types of forces that are acting on it. And so right here, we have the two types of forces. We have conservative and non-conservative forces. A conservative force is when the work done in moving an object between 2 points is independent of the path taken. What this means is that the work that happens when moving an object, it doesn't matter so long as it starts at the same starting point, ends at the same ending point. So how it gets there doesn't matter. What I can give as an example is, say I have 2 points, point A over here and point B over there. If my force is non-conservative, The work required for it to go from A all the way down to B for motion 1 would be the exact same as if it started at A, went around B, looped up to A, and then went down to B again. It doesn't matter on how it gets there, so long as it gets from point A to point B. That's essentially what a conservative force is. We do have examples of conservative forces. Those would be the forces due to gravity, electrostatics, and elastic spring forces. And we know that whenever we have conservative forces, our mechanical energy is conserved. So our change in mechanical energy is 0. Now, let's look at non-conservative forces. For non-conservative forces, the work done in moving an object between 2 points depends on the path taken. Mechanical energy is not conserved in the case where we have non-conservative forces. And therefore, we have a non-isolated system whenever we have non-conservative forces. Right. Examples of these would be applied or tension forces, friction, or air resistance. Friction removes energy from the system. Applied or tension forces kind of add energy into the system. And so for non-conservative force, let's think of it this way. If I have a box and it has to travel across a surface, if I take my box from point A over here to point B once, if I take it once, like I have one trip, I have a certain work done. But if I go back and forth many times, then the friction kind of adds up. It's not going to be the same. You're not going to have the same work, if that makes sense. We don't have to understand the nitty-gritty of it. I think for the purposes of matric, as long as you know how to identify conservative and non-conservative forces, as well as knowing when to apply the appropriate formulas, you should be sorted, you should be great. Cool. So let's carry onwards. Let's get into the equations. And now we have here the first equation. The work due to non-conservative forces is equals to the change in kinetic energy plus the change in potential energy. The non-conservative forces, you would just consider your work due to friction or your work due to gravity. And then for your mechanical energy, the formula is just given there, just to jog your memory. That is the sum of the kinetic energy and the potential energy. Cool. Over there, we have the diagrams I attached, explaining what I was saying in the previous slide, whereby the work done by gravity in this scenario over here is exactly the same. The work done by gravity is going to be calculated as, let me rather switch to my white pen. We'll have work by gravity is equals to minus mgh, where h is our vertical displacement. Right, and then if we look at the second scenario given over here, the friction varies. Sure, we may have the same distance between the centers for the two boxes over here, but for the second box, the path is longer, so there's going to be more work due to friction as compared to that one over there. We know a straight line is shorter than a curved line in this case. Granted that the distance between the centers is the same, but the one will travel a longer distance, so it will have more work done due to that. Cool. So let's carry onwards. Over here, we have further formulas for the net work. We have the net work is equals to the work of the applied force plus the work of the friction force plus the work due to gravity. We also have, underneath that, the net work is equals to the change in kinetic energy, as well as a third formula telling us that the net work is equals to the net force multiplied by our displacement multiplied by the angle at which our displacement or our force is acting. I have over there the work due to gravity is equals to mgh. Yeah, let's carry on as we have an example attached over here. So really, the work energy theorem, the cases under which you'd mainly use them is if they ask you guys to find the velocity values of, let's say, an object as it slides down a slope or something along the likes of that. We usually use the work energy theorem when finding velocity values, or if they give us velocity values and we have to find something else. All right, let's look at our example. We have a 1,200 kilogram car traveling at 20 meters per second, and it applies its brakes. And friction does negative 80,000 joules of work. Using the work energy theorem, calculate the final velocity. And for this one, we can simply plug it into the formula. For the kinetic energy over here, I just broke this down into our kinetic energy final minus our kinetic energy initial. And we know that to find the kinetic energy of anything, that's going to be equals to half times our mass multiplied by our difference in velocities squared. So we have Vf squared over here minus half m Vi squared. Okay, all good. Let's carry onwards then. Yeah, right here we have the three cases on which we would apply the work energy theorem. Is the sound, I take it that the sound isn't that great. Is it better now? Can I get a thumbs up, thumbs down? Okay, cool. Right, so to calculate the F net, typically you add the work done by each of the forces. So you do your work due to applied force, your work due to friction, and your work due to gravity. You sum all of that up, and then you end up getting your net work. You can also find F net, or you find F net if you already have your network from what I explained in the previous step. And then all this can be done to find the velocity values in the third step when doing your work net is equal to your change in kinetic energy. I'd say it's a simple, clear-cut process. It doesn't get that difficult, to be honest with you, but we'll see later when we start doing the questions, which would be now in actual fact. So we have the first question given here. We are told that a crate of mass 3 kilograms is at rest at point A on a frictionless horizontal surface. A constant horizontal force of 12 newtons acts on the crate and moves it from point A to point B. The crate then moves down a rough plane inclined at 20 degrees to the horizontal. The distance from point A to point B is 7 meters, and from point B to point C is 8,6 or 6,8 meters. As shown in the diagram below, we have the diagram over here. And now let's get started. Let's use the energy principles only to calculate the kinetic energy of the crate at point B. So with this one, it's a 3-mark question. That means 1 mark for the formula, 1 mark for the substitution, 1 mark for the final answer. I trust that you guys will be able to do this one. Let's see. For a 3-mark question, we should be taking no more than 3 minutes. In the meantime, I will be doing the question as well, and let's see who gets it or who finishes quicker. I'm going to start off by selecting my formula to use. In my case, I'm going to do the work due to non-conservative forces. And that's going to be equals to our change in potential energy plus our change in kinetic energy. For the motion between points A and points B, there is no change in height, so we don't have a change in potential energy. So I'm just going to put 0 in place of that. But we do have a change in velocity. Remember, we were told that our crate starts at rest at point A. I'm going to highlight that over there. And we have to keep this in mind when substituting in our values. We also know that between points A and points B, the only non-conservative force that is acting is our applied force. We are told that it is frictionless between points A and points B. So that then means that the work that's happening here is our work. I'm just going to have WA for work applied. That's going to be equals to our change in kinetic energy plus 0. I'm then going to expand the equation. I'll then have my applied force. I'll just have it as FA is equals to half m VF squared minus half m VI squared. We know that we start at rest, so our initial velocity is 0. And so that means all we're left with is the final kinetic energy. We scroll a bit downwards. And yeah, if we substitute in our values, we end up with the following. I'm going to have 12 multiplied by 7 multiplied by cos of 0. You could leave cos 0 out. It'll still give you the same answer. You just need to know when things are negative or when things are positive. And that's going to be equals to, not too sure what happened there. Sorry about that. That's going to be equals to half multiplied by our mass in this case is 3 kilograms multiplied by our final velocity. At this present moment, we don't need that per se because they did ask us to get the kinetic energy, our final kinetic energy. And so I'm just going to write EKF over here, actually. We then end up with a final kinetic energy of 84 joules. Quite straightforward. Let's carry on. Let's look at the following. It goes on to say that force F is removed when the crate reaches point B. The crate then experiences a constant frictional force of 21 newtons as it moves down the incline. Let's start off by drawing a free body diagram showing all the forces acting on the crate as it moves down the incline. This has a 3-mark allocation, and whenever we see a 3-mark allocation specifically for free body diagrams or any mark allocation for free body diagrams, it gives us a hint as to how many forces they expect to see in the answer. So for our free body diagram with a 3-mark allocation, we expect to have 3 forces. I'm going to draw it right here. I'll have my force due to gravity over here, Fg. I am going to have my normal force over here, which is perpendicular to our surface. I'm just going to have the dotted line just to represent the surface. And I will have my force due to friction right there. Cool. Remember, guys, we were told that it is a rough surface between points B and points C. We do have constant frictional force between points B and C. Great. Now, let's get to using the energy principles only to determine whether or not the crate will pass point C. So this one, guys, I wouldn't say it's a complicated question. We just need to know what exactly we're looking for. In this case, it'd be easiest if we just figure out the displacement of our crate as it slides down the inclined slope. I'm going to start off by working with my network formula. I'll have, let me rather start here. I have my network is equals to my change in kinetic energy. Cool. As we slide down the slope, remember guys, our work happens whenever there's displacement. So for this case, the forces that are acting along my axis of displacement, that'll be my force due to friction, as well as my FG parallel. My parallel component of my force due to gravity will be looking like that, be in that direction essentially. So let's get to expanding this equation. We'll have my work due to FG parallel plus my work due to friction, and that's going to be equals to my change in kinetic energy. Right, from here, let's go further and expand the equation even more if we can, or we can in this case. So now we want to find out if it'll pass the point C. We know at some point it's going to stop. At some point it'll stop, the friction is acting. In our case, I'd say our friction should be roundabout greater than our, well, I wouldn't say greater, but our friction is acting on our crate as it slides down the slope. It's going to stop because of that friction. We need to figure out where. Does it stop before point C or does it stop after point C? So now I'm going to take my final kinetic energy as 0 for when my crate stops to find out what is the displacement at the point where it stops, or from point B up until the point where it stops. Hopefully that is making sense. Let's go further. So my FG parallel for my work due to gravity along that axis, the dotted line, I'm going to have M times G, my mass times G, times sine theta. And that's going to be multiplied by my displacement. I'd have it as 6,8. And to that, I'm going to add the work due to friction along that plane. I'll have it as 21 multiplied by 6,8. And then that is then going to be equals to the change in kinetic energy. Cool. Let me get to substituting into the work side of the formula or of the working out. I'll have 3 times 9,8 multiplied by sine of 20 degrees. If I take the parallel component along that axis, and that's going to be multiplied by 6,8. To that, I'm going to add what I have at the top, 21 well, it's not going to be add, in actual fact. It should be, yeah, actually, it's fine. Sorry about that. So to that, I'm going to add my 21 multiplied by 6,8, and that is going to be equals to, I'll have the 0 minus 84. Remember, we found the kinetic energy at point B to be 84 joules at point B. Great. Let's now get to figuring out what my displacement is. For this one, so I should rather have this equals to my EKF. Actually, no, 0 is fine. I'm solving for my displacement, so I should have my delta x in there. Just a minor hiccup, sorry about that. Right, so like I mentioned previously, we're solving for delta x to see if it's greater than or less than 6,8, to see if it stops before or afterwards, or maybe it stops at point C. We're setting our final kinetic energy for 0 as 0 to be the point at which it stops, and we're solving for delta x. Yes, now everything is fine. If we put this into the calculator or we do all the algebra, we'll end up getting a value of delta x being equals to 7,68 meters. And we know that 7,68 meters, that is greater than 6,8. And so we'll then end up passing point C. So yes, our crate does pass point C. Hopefully we're all good with that question and we can move onwards. Our next section that we're going to do after this is going to be power. Do we have any questions on this? Can I explain it again? Sure. So for this question, we have to keep in mind that we found our kinetic energy at point B to be 84. So we'll take that as our initial kinetic energy. Now, we want to find out if our crate will pass C or not. But what we can do is find out the total displacement of the crate along the slope up until the point it stops. Or in other words, our kinetic energy is 0. Our crate would be falling down the slope. And as it falls, it slows down until it reaches a certain point. We need to figure out, is that point at which it stops before or after point C? That's why I have my EKF set as 0 over there. And so maybe it would be beneficial if I write it a bit more neatly. So I have here my net work being equals to my change in kinetic energy. We all good on that? In this case, we're dealing with the forces acting along our axis of displacement, which is the dotted line. So I'm only going to use my FG parallel as well as my force due to friction to get the work or my net work that happens. That's why my network, I expanded it to become work due to FG parallel plus my work due to friction. And that's going to be equals to my final kinetic energy, EKF, minus EKI, right? Our initial kinetic energy is 84 joules. Our final kinetic energy, we want to set it to be 0 because at 0, our crate stops. it stops moving, slows down. Our crate rolls or slides down the slope until it stops. We want to figure out how far does it slide down up until the point it stops, and that's how we have our final kinetic energy as 0. Cool. So I'm going to put my 0 here. My initial kinetic energy will be the 84 that I calculated earlier, and all that's left for me to do is essentially expand the work variables over here, my work due to FG parallel and my work due to friction, and I want to end up solving for my displacement delta x. Is that a bit clearer? Can I get a thumbs up? Cool. I'm seeing thumbs up, which is quite encouraging to see. Hopefully you guys are still attentive and we are ready to carry onwards. Let's look at power. Power, when it comes to the work, energy, and power. Okay, somebody's asking why aren't we adding cos theta? We taking the movement along the slope. Why aren't we adding cos theta? I'm not too sure. We just need to note what exactly is happening. So we need to know if it's parallel to the axis, will it be negative or positive, and deal with it as such. Cos theta, when it comes to the work, is equals to F delta x times cos of theta. This theta applies to the, or refers rather, to the angle at which my force is being applied and not necessarily the angle of incline. Yes, my angle of incline is 20 degrees, but that's not the angle on which my force is being applied if I'm only considering forces that are acting along my axis of displacement. So if I'm only considering the forces that are acting along this axis and everything is acting parallel to that, we're not gonna necessarily add cos theta. Is that making a bit more sense? We should note that if we're taking the motion along the axis, if we're setting down the axis as positive, anything that is acting up the axis over there, if we have that as, we should have that as negative. If everything on this side is positive, everything there should be negative. And so we know that our work due to friction, if you do want to consider your cos theta, we'd either have 0 or 180, 0 being the stuff that's acting down the slope in the direction of displacement. Our theta would be 180 for everything acting up the slope, because that's opposing our displacement, and that would end up making our values negative. So, yeah. Is that a bit clearer, Khadija? Okay, cool. So do note that I put a negative here to account for my force of friction being up the slope as opposed to down the slope, which is positive. Great. Let's carry on then, guys. Let's move to power. We still have more work, energy, power questions at the end that will challenge us and put our knowledge to the test. Power isn't really a complicated or complex thing to do. We know power is defined as the rate at which work is done or energy is expended. That is measured in watts. If we get into the equation over here, we have power being equals to our work over the change in time. We also have another formula given for our average power being equals to our force multiplied by our average velocity. And that version is extremely useful in the case that something moves at a constant speed along a rough horizontal surface or inclined plane, typically. Let's get to the example over here. I think this one, you guys can try it out. A Bucky's engine exerts a constant driving force of 3,000 newtons while traveling up a hill at a constant speed of 15 meters per second. If it takes 20 seconds to climb the hill, find the work during this period. So you want to start off by, I'd say, finding the power, then you can find the work. We can use the average power formula in this case because we are driving up a hill. We're just going to say that the hill's surface is rough and we have a constant speed. So our average velocity will be 15 meters per second. Why don't you guys try this one out and let me know what the answer is? What do you guys think the work of the Bucky's engine up the slope for the 20 seconds during which it's moving will be? I'm just going to start off by writing the formulas necessary for this. And then hopefully you guys can take it from there. So step one, we typically have our P average is equals to our force times our velocity average. Let's find the power. And then our next step would be to get the work from the given formula over here. Please remember, when answering physics questions, always write down the formula that you use. We do get marks allocated to just writing down the formula. So what do you guys think the work of the Bucky's engine up the slope during this period will be? This question should take about, I'd say not more than 4 minutes. We have an answer over here. That is 900,000 joules. That is correct. Well done on that. So for this one, it's a simple plug and play type of question. We just substitute in our values to end up getting our work. So well done to everybody that tried. I'm just going to fill in the formula or substitute in my values here. We will end up with 3,000 in place of F and 15 in place of our velocity. That then means the average power as the Bucky travels up the slope, that'll be 45,000 watts or 45 kilowatts. I'm just going to write kilowatts. Right. Now from here, in order to get the work of the engine as it moves up the slope, I'm just going to substitute in the power value that I found previously into the next equation. That'll then be 45 times 10 to the power of 3 multiplied by our time, which is 20 seconds. That then gives us a value of our work being 900,000 joules or 90 kilojoules. Oh, 900 kilojoules, sorry. Yeah, the answer is 900,000. Well done to everybody that tried. Let's move onwards then. Now let's get to questions. We're going to start with a trickier question or a more challenging question. So we have the following scenario over here. It states that learners conduct a test Just want to, yeah. So learners conduct an experiment to determine how the initial kinetic energy given to a trolley affects the distance the trolley moves on a rough horizontal surface. A learner pushes a trolley of unknown mass until it reaches point A with kinetic energy EKA. The horizontal distance, delta x, traveled by the trolley before it comes to rest is then measured. See the diagram below. So there's a diagram kind of showing us what the experiment kind of looks like. We have the trolley, we have point A over there, and then we have delta x. They say that the experiment is repeated with the trolley moving on the same rough horizontal surface, but with different initial kinetic energies at point A. Draw a free body diagram showing all the forces acting on the trolley during its motion after passing point A. Again, guys, whenever we see a 3-mark allocation or any mark allocation for free body diagrams, they are telling us how many forces they expect to see. We have a 3-mark allocation for this free body diagram, so we should be having 3 forces. What do you guys think those forces are that are acting on the trolley for the motion as described in the question? Any ideas? Yeah, we have FG, that's one of them. We also have our normal force and we have our force of friction. Well done, guys. So our FG is over here. We have our normal force and we also have our force of friction. Cool. 3 marks, 3 forces. Great. Now, what do you guys think the independent variable in this experiment is? How do we identify the independent variable if they give us a plot? What is the independent variable over here? The hint would be to look at the graph given on the right. Yeah, our independent variable is the initial kinetic energy. So I'm just going to write here initial kinetic energy. Simple enough, right? But let's get to the challenging questions or let's get to the more challenging questions, the ones that are actually going to make us think a little. Cool. So right here, they want us to calculate the mass of the trolley if the coefficient of kinetic friction between the wheels of the trolley and the rough horizontal surface is 0.18 for 6 marks. Do we have an idea of what we're expecting to see? Do you guys have an idea of how to approach this question? Because we're going to have to interpret the graph and get the necessary information from there in order to solve this. Let's see. Does anybody have an idea? Maybe we can put a thumbs up if you do have an idea of how to solve this. Maybe a thumbs down if you don't know whatsoever on how to even begin with this question. How would we solve this question, guys? You don't have to answer per se. I just want to see maybe a thumbs up, thumbs down to see if you guys can kind of figure it out, if you have an inkling on how to approach this. Some people are putting thumbs up. Let's see. So I'm going to show you guys 2 approaches for this one. The first approach will be me interpreting this as, I'd say, well, I'm going to interpret the straight line graph that they give to us, and I'm going to get the necessary information from there. Cool. So from the straight line graph given over here, or we know that the property of any straight line graph is that the gradient is a change in y over the change in x, isn't it? So I'm going to have m is equals to delta y over delta x. But what would that even mean in the context of this question? Let's get into it. So over here, my y in this case is delta x. Let's try not get confused on this. Our y variable is x. Right. So I'm gonna have delta x at the top, and at the bottom, I'm gonna have my change in initial kinetic energy, which is just EKA. Well, I'll write it out in full, and then you'll see exactly what I mean. This is going to be equals to delta x over EKA minus 0. Remember our initial. Well, I'm going to take the initial as this origin point over here. Okay? Cool. This then simplifies to become delta x over EKA. But at this present moment, it's still not really clear as to what we're dealing with. Now, is it? Let's jump to the net work formula. Hopefully that will clear things up a bit. We know that the net work is equals to F net multiplied by delta x multiplied by cos of theta. In this case, theta is 0. We're just going to take that motion over there. And so if I have cos 0, that's 1. So that's the same as me writing F net multiplied by delta x. And then I have my network over here. And even at this point, maybe it's still not explicitly clear on where I'm going, but we can make the necessary relations to make sense of what I have written over here. Cool. Let's also recall that my network is equals to my change in kinetic energy, isn't it? Maybe now you guys can kind of spot where I'm leading with this. This then means I can substitute this value over here, or I can substitute this expression into that over there. I'll then have delta EK is equals to F net delta X. Is that a bit clearer now? I can only write this because I know that delta EK is equals to my net work done. That's just a given formula. And that is also equals to F net delta X cos of theta. So I just kind of matched two equations to make relationships between what I want to see in particular. Cool, let's carry onwards. I want to now isolate F net, or put EK and delta X on one side. This then means that delta EK over delta X is equals to F net. I can also write this as delta X over delta EK is equals to 1 on F net. Now can we see where exactly I'm going? I can make this relationship. I have delta X over delta EK here. That is equals to that there, which therefore means that we are finding 1 on F net if we find the gradient. Now I'm going to actually go on to substituting in values. Let me now come up here and let me take the point this one over here given with my delta x as 1 comma 5 and my initial kinetic energy as 6. This then means that I have 1 comma 5 over 6 over here. Well, it's actually 1 comma 5 minus 0 over 6 minus 0, which is still the same as 1 comma 5 over 6, which is 1 over 4. Okay. Now, at this present moment, can we see where we're going? Do you guys see the relations that I'm making in order to actually make sense of the given question? I guarantee you it's not something that is unsolvable. It's just challenging in the sense that it requires you to think outside of the box. So let's get to solving this question. I can therefore state that my 1 on F net is equals to 1 on 4. Therefore, F net is equals to 4 newtons. But you may be asking me, what does that help me with? Why am I looking for F net? I'm looking for F net so I can use that to find my force of friction that I will then use to find my mass of the object. Because we can make a connection or a relation between friction and the mass of an object if we have the normal force. All right? Cool. Now let's carry onwards. I'll have maybe in this little box, just to separate the stuff, just to show you guys what the final stretch of this question looks like. Let me write my force of kinetic friction formula over here. I have FFK is equals to my coefficient or kinetic coefficient of friction multiplied by our normal force. In this case, my normal force is just mass times the acceleration due to gravity, because my normal force is parallel, or not parallel, perpendicular to the surface, and the surface is completely horizontal in this question. So I'm going to have my coefficient due to kinetic friction over here multiplied by mass multiplied by gravity, and that's equals to FFK. Now, let's go back to the free body diagram that we drew of our trolley as it moves right up here. If we're only considering the forces acting horizontal, the only force here is my force due to friction. That therefore means my F net is the force due to friction, because that's the only thing that's happening, or the only force that's acting along the x-axis. Okay, are you with me so far? I can therefore state, or let me write here at the bottom, therefore F net is equals to FFK, which is equals to 4 newtons. It's getting a bit cramped, sorry about that. I can put the 4 newtons over here, and I can then end up solving for my mass. If I just substitute in the other values, I have 0.18 as my coefficient of kinetic friction. That's going to be multiplied by our mass, multiplied by 9.8 over here. And that if we put this into the calculator, let me do that right now. Let's see what we end up getting as a value. I end up getting a value of 2.27 kilograms. Cool. That's the end of this method. There's a question, you're a little lost because you're not used to manipulation or long methods. Well, this is a 6-mark question, so granted, it's gonna be a bit more complex. Over here, what specifically are you lost on? Is it you because you can't necessarily see why I've made the relations that I've did or that I've done? Or is it something else? Because we start off by interpreting the graph to see what the gradient gives us. The gradient gives us delta x over my initial kinetic energy, or in this case, delta x over delta initial kinetic energy. From then, I want to now find relations I can make to make sense of the graph that I'm given. I have my net work is equals to my net force multiplied by delta x multiplied by cos theta. And from then, I just did all that manipulation, went all the way to the end, and found my mass as 2.27 kilograms. That is one of the methods. The other method is a bit more straightforward or a bit simpler or quote unquote easier to follow along with. Is anybody still viewing this? Can I erase it? Can I get a thumbs up? Would you guys like to see the second option on how to work this out? If you'd like to keep this, just grab a quick screenshot now. I am going to erase. Okay. Let me get to erasing then. Or rather, I'd maybe just minimize it or make it smaller and push it to the side. Now, let's go through a more quote unquote traditional way or more comfortable way on how to do this. We're still going to start off with our formulas when it comes to work. We can choose any of them. Well, not necessarily any of them. I'm going to choose you can choose either your network formula or your work due to non-conservative forces formula. It's all going to work out to be the same. Let's do our network formula. This one, you can never go wrong with this one. So long as you apply your stuff properly, you can never go wrong with this one. We have our network being equals to our change in kinetic energy. You could also write it as your work due to non-conservative forces is equals to your change in kinetic energy plus your change in potential energy. But we know that since our trolley does not move along the y-axis, it doesn't displace vertically, our change in potential energy is going to be 0. So I'm just going to have this over here. Now, again, when it comes to the network, we have to remember that only friction is acting on the x-axis. It's only friction happening along the x-axis, okay? So I can then write my work due to friction is equals to my change in kinetic energy. So far, so good, I'm assuming. Let's carry onwards. Let's break down this formula or expand it essentially. I'll have my force due to friction, FF or FFK, force due to kinetic friction, is being multiplied by my displacement, delta x, multiplied by cos of theta. Theta is 0 degrees. If ever the theta stuff confuses you, I'd like you to think of it in this way. If you have, just going to digress a bit, if you have your axis over there, right? Let's say you have your horizontal axis, your universal horizontal axis over here, and your force is acting, let's say at this angle there. We always take the anti-clockwise, that will be theta. And so if we go on our horizontal global axis and we have a force that goes in this direction, this is 0 degrees. Our force hasn't moved. This angle here would be 0 degrees. That would give you cos 0, which is 1. Whereas now, if you're moving in the opposite direction, your angle would then be 180 degrees, and cos of 180 is -1. For those who are confused on how exactly we do with the theta, it's about the angle of application of our force. That's what's happening over here. Are we all good on that? Hopefully that helps somebody. Let's carry onwards. Let's go back to the question. I'm still expanding my work net formula. On the left, I have my work due to friction. And then on the right, I have my change in kinetic energy. My change in kinetic energy, I'll have as EKF minus EKI. Let's go back to the scenario given. We are told that the learners conduct the experiment by pushing the trolley. They let go of it at point A. And then from then, our trolley travels a distance of delta x before it comes to rest. This is the key piece of information we cannot miss. It comes to rest, and then the displacement is measured. So if it comes to rest at the end of the motion, we know our final velocity is 0. That then makes our final kinetic energy 0. But I'm still going to write all the stuff here and substitute in just so you guys can see exactly what I'm referring to. So our EKI, I'll just keep it as EKI. And then my force due to kinetic friction is going to be -F multiplied by, now in our case, my displacement, delta x over here. Cool. Now I have to choose a point to substitute in. I'm just going to substitute in this point again. I'll then have minus f multiplied by 1,5 as the delta x is equals to half times my mass times 0 squared, which is just going to be 0, minus, now my initial kinetic energy for that chosen point is 6, and I end up with minus fk is equals to minus 6 over 1,5. Therefore, FFK is equals to 4 newtons. Don't know why I'm writing delta. Right, and now from here we can go into doing the net force, the normal force, and the kinetic friction formula, where we have FFK is equals to our coefficient of kinetic friction multiplied by Fn, which is then our kinetic coefficient due to friction multiplied by our mass multiplied by G. And because we know that our FFK is 4 newtons, and we know that this is 9,8, and that over there is 0,18, our only unknown would be the mass, and we can still solve for the mass. Where we have our mass is equals to our kinetic force, our force due to kinetic friction, FFK, being divided by our coefficient of friction multiplied by G. What about the second method? How do you feel about that? Are we good? Can I get a thumbs up? Cool. So let's carry onwards. Let's move to the next question. Now, for the next one over here, this one I'd say is a bit better. We are told that a constant force F is applied at an angle of 30 degrees to the horizontal on a crate of mass 6 kilograms that is initially at rest as shown in the diagram below. A constant frictional force of 10 newtons acts on the crate as it moves from rest point A along the horizontal surface to point B. The distance between point A and point B is 1.5 meters. The speed of the crate at point B is 2 meters per second. Now, let's get to drawing our free body diagram showing all the forces acting on the crate. Let's look at the mark allocation. How many forces do we expect to see, or how many forces should they be on our free body diagram? What do you guys think? Based off our mark allocation, how many forces should they be on our free body diagram? Okay, are we still there? No answers in the chat. Let's carry on. So we have a 4-mark allocation. Thank you for all those answering. We have a 4-mark allocation. We expect to see 4 forces in the free body diagram. Cool. Let's get to drawing it. What are the forces? Which forces do you guys think you'll see in the free body diagram? What are the 4 forces? Yeah, we have our normal force, force due to gravity, force applied, and our force due to friction. So I'm going to draw that in. Thank you for answering. Right, so this is going to be our force applied. This is the one at the bottom here is our force due to gravity. This is our normal force, and that right there is the force due to friction. Cool. We have our four forces over here. Now let's get to the next question. Let's use the energy principles only to calculate the magnitude of force F. This is a 4-mark question. I'd say it's not as complicated as you guys would think. This one genuinely is formula, correct substitution, and then answer. So why don't you guys try this one out? For 4 marks, try it out. This should not take you more than, I'd say, essentially 2 minutes. So try that out and drop your answers in the chat. And let's see who's going to be the first to answer it, who's going to get it right, and whoever doesn't get it right, we will explore how exactly to approach questions like this. So with this one, maybe 2 to 3 minutes to get an answer as to the magnitude of our applied force. If you have any questions, do drop them in chat. This is the perfect time. How are we feeling now with the session? Are we feeling a bit better about work, energy, and power? What's up? We have an answer. Our answers are starting to roll in. We have 20,77. Let's see. Do we agree with this answer? Do we get the same? Do we get different? Where are we at with this? I'm just going to wait for maybe a few more people to answer, and I will explore the solution. All right, the answers are rolling in. 20,77. That is correct, guys. Well done to everybody who got that. Whoever didn't, let's explore the solution right now. So let's get to it. I'm going to start off by I'm going to write my network is equals to my change in kinetic energy. Guys, if you write the correct formula, you guarantee a mark. That's just how it works. The correct formula guarantees your mark. Cool. Now from here, my network, I can break this down into the work due to friction, or my work due to the applied force, plus my work due to friction. So I'll have my WA for my work due to applied force, plus my work due to friction, and that's going to be equals to my change in kinetic energy. In this case, I'm just going to expand this to be half m Vf squared minus half m Vi squared. Cool. Now I'm going to start substituting in my values. For the work due to my applied force, I have to take my horizontal component, which would be this right here. I have to take my horizontal component of the applied force. So I'm then going to write my FA multiplied by cos of 30 degrees. Remember, for this, I'm just using regular trigonometry, where we have sine is opposite on hypotenuse, cos is adjacent on hypotenuse, tan is opposite on adjacent. I'm going to have my right angle triangle over here, this being my angle theta. And since I'm looking for the horizontal one, which is the bottom, I'm looking for adjacent, and I'm given my hypotenuse, which is the applied force. Let's carry onwards. So I have F multiplied by cos theta multiplied by my displacement, 1,5. And then this is going to be multiplied by cos of 0. Cos 0 because, well, I wouldn't say cos 0. I don't need to put cos 0 in this case because I'm taking the component, the horizontal component. Now, to this, or from this, I'm going to subtract my work due to friction, which is going to be 10, my constant force of friction given over here, multiplied by my displacement, 1,5. And now in this case, I'm not going to put my cos theta because I already put the negative. But if I didn't put the negative, I'd have to put cos 180 over here, because you know that the friction is opposing the direction of motion, with left being negative, right being positive. So I can have it as this, or I can have it as that, whichever one you choose, so long as it makes sense. Let's carry onwards. This is then going to be equals to half multiplied by the mass, which is 6 kilograms, multiplied by our final velocity, or velocity at point B, is 2 meters per second. So I'll have 2 squared. And I'm gonna then subtract 0 because we're given that it is initially at rest. So when you read questions, highlight this information. Highlight at rest and the point at which it's at rest. Highlight the other given values. They wouldn't tell you information if they don't expect you to use it. Cool. Now, from here, all that's left is algebra, and I end up with a value of FA being equals to 20,78 newtons, or 77 newtons, roundabout. Let me do this. Okay, so how do you feel about that question? Are we good? Are we sorted? This was a simpler one in my opinion. Now let's move on to a theory question now. We are told that a 2-kilogram object is placed in the crate. What effect will this have on the work done by the same force F when the crate is again moved from point A to point B? Will it increase, decrease, or remain the same for 2 marks? I want you guys to state increase, decrease, or remains the same, but I also want you guys to substantiate your answer. I want you guys to explain to me why you think it increases or why you think it decreases. So let's see. What do we think is happening over here? If we add a 2-kilogram mass in the crate, making our total mass 8 kilograms, will the work done increase, decrease, remain the same? And why? Okay, somebody answered remains the same. Do we agree with Tabo? Do we agree? Do we think that it increases, decreases, or remains the same? Okay, so guys, our net or our work done by the force in this case, that remains the same. It remains the same, and let's explore why exactly that is. So I'm just going to highlight remains the same, and I'll show you why. So we need to remember, or we need to use a formula. I'm going to use a formula to explain the answer. I have my work being equals to my force multiplied by displacement multiplied by cos of theta. We're not changing the angle. We're not changing the force. Our displacement x, I'd say, also isn't changing. Over here, we can clearly see that our network, or not our network, our work in this case, due to the applied force. So let me make that a bit clearer. The work due to the applied force is directly proportionate or proportional to the force that's applied. But we know our force isn't changing. We also know that the work of the applied force is directly proportional to the displacement, but we're not changing the displacement. So nothing is changing in this case that would make our work change. So our work is gonna remain the same. Are we good on that? Can I get a thumbs up? Are we good? Are we sorted? Can we carry onwards? Great. Now, let's move on then. The next question over here reads as follows. An object of mass 1,8 kilograms slides down a rough, curved track and passes point A, which is 1,5 meters above the ground, at a speed of 0,95 meters per second. The object reaches point B at the bottom of the track at a speed of 4 meters per second. And the diagram is given over there. Let's name the conservative force acting on the object. Now we're doing a callback to the revision we briefly did before the questions. What is the conservative force acting on our object? That is correct. Our conservative force over here is the force due to gravity. So I'm just going to write Fg. Our follow-up question, is mechanical energy conserved as the object slides from point A to point B? Yes or no? And what's the reason? So you guys in the chat, just drop a Y for yes and for no. Yes, no. Let's see. Is mechanical energy conserved? Yeah. Answers are rolling in. Mechanical energy is not conserved because there is friction on the rough inclined plane. Whenever there's the presence of a non-conservative force, know that mechanical energy is not conserved, and therefore we don't have an isolated system. It's a non-isolated system in that case. This is a callback to the revision we did initially. Right. Let's carry onwards. So I'm just gonna write over here, no. The answer is there is a non-conservative force. Which is friction in this case. An applied force counts as a non-conservative force also. Let's carry on. Let's calculate the gravitational potential energy of the object when it was at point A. This is a 3-mark question. So it is a simple formula, substitution, answer type of question. This is 3 marks. What do you guys think the value of this is? Okay, answer's already in. Well done. Great. Thank you, Wenzile. The answer for this one is 26,46 joules. So the gravitational potential energy when it passes point A, we find it by using the following. We have EP is equals to mg delta H. We're going to take ground as 0, and we take 1,5. Well, it's not delta H, sorry. It's just mgh, yeah. So ground is reference 0, and then anything above that is positive. If you calculate this, we end up with 1,8 multiplied by 9,8 multiplied by 1,5 meters. And then this then gives us a potential energy of 26,46 joules. Well done to everybody that got that. Let's move onwards. Let's see. Now we're told to use the energy principles to calculate the work done by friction on the object as it slides from point A to point B. So we're going to have for this question at the present moment, A is our starting point, B is our ending point. we need to keep in mind the information they told us previously, that it passes point A at a speed of 0.95 meters per second. So what do you guys think that is? Initial or final velocity? Velocity at A or velocity at B? That's going to be the velocity at A. Cool. This is, well, not velocity, this is speed, sorry. 0.95 meters per second. And then they give us another speed, which is 4 meters per second. That's going to be for the speed at point B. So over here, I'm just going to write 4 meters per second. And now let's use the energy principles to calculate the work done by friction. So for this one over here, we have, well, essentially, we have kind of two options we can take. We can do the work net, or the net work done by all forces, or we could do the work due to non-conservative forces. I'm going to use the work due to non-conservative forces. I have the following over here. The work due to non-conservative forces, that's going to be equals to delta K plus delta U. The only non-conservative force acting between points A and points B is the friction from the rough surface. So I'll have WF over here on the left of the equation. On the right, I'm just going to expand my kinetic energy. Let me fix this. Let me write it as EK. I'm going to expand my kinetic energy and potential energy, just writing it in other forms, and have it as the following. I'll have half m VF squared minus half m VI squared for the change in kinetic energy. And to that, I'm going to add my change in potential energy, which is mg, and I'll have delta H. Let's go further. I'll end up with half of my mass over here is 1,8. Well, before I get there, let me just kind of make it a bit simpler to follow along with. I just factorize the half m from those two terms. And to that, I'm going to add mg hf minus hi. Guys, be sure not to forget these squared values or mess it up and like maybe put it over here. You'll end up with a totally different answer. Let's carry on then. If I substitute in my values, I end up with half times 1,8 multiplied by, in brackets, 4 squared minus 0,95 squared. And to that, I'm going to add, I have my mass, which is 1,8. My acceleration due to gravity, which is 9,8. And then in the brackets, I have my final minus initial. My final is 0. My initial is 1,5. So essentially, this over here, if you work it out, it's going to be exactly the same value, or should end up being exactly the same value as that right there. I think that that's genuinely the reason why they asked you to calculate it previously. Let's carry on then. If we now solve this, put into a calculator, you'll end up with a value of minus 12,87 joules. Yes, well done to everybody that tried this. We do get a negative answer, which does make sense. We are removing energy from the system. We're losing energy due to heat. Or we lose energy because of the friction that energy is converted into heat, that heat radiates away. I will go to this question. Can I get a thumbs up? We do have time to perform or to do one more question after this. That's what we're going to do. Great. Hopefully everybody is feeling a bit better about work, energy, and power, and we understand where to apply the principles, or when and when not to apply the principles. So let's move on. Note here that they gave us velocity values. We had to use the work energy theorem to find whatever they were looking for. Let's move on. Last question over here. This is a theory question just to test your guys' understanding. What is the value of the net work done on the object as it slides from point B to point C? This is purely theory. What is the value? For 1 mark, shouldn't even take us 1 minute to answer this. So what do you guys think the value of the work between points B and C is? Any ideas? Even if it's a random guess. That is correct. The answer is indeed 0. So the work due to friction between points B and C is 0. So let me write it, the network. So between points B to C, the network is equals to 0 joules. We can never forget the units. The reason as to why the network between points B and C is 0 is because there's essentially no net force acting between those 2 points. There was a net force acting when we were sliding down the slope. We had friction, and we also had displacement due to gravity. So we had work due to gravity because it was displacing vertically. Now, between points B and C, there's no vertical displacement, so we have no work due to gravity. And then if we draw a free body diagram of the object between points B and C, we'll see that we only have Fg and Fn. No friction happens because BC is frictionless and we have no applied force. That's why the work or the net work between points B and C is 0. Are we all good on that explanation? Yes, the object is moving between points B and C, so there is displacement between B and C, but there's no net force along the x-axis. Great, let's carry on then. This would typically be a 1 mark question. This is 1 mark allocated to this one. Let's carry on then. Let's go to the next question. Now, a 12 kilogram block is initially at rest at point A at the bottom of a rough inclined plane. The block is pulled up the incline by a constant force F acting parallel to the incline. The block reaches point B, which is at a vertical height of 4,5 meters above the horizontal, with a speed of 2,25 meters per second. So I'm just going to highlight the values because we are going to use them at some point. And yeah, constant F, maybe that's worth noting. And then we have a rough incline. So there's friction. Let's draw a free body diagram for the block when it is pulled up the inclined plane. We have 4 marks allocated to this question. We are therefore expecting to have four forces in our free body diagram. Our four forces will be Fg, our force due to gravity. We'll have F over here, our applied force. We're going to have Fn, which is perpendicular to the slope. Just draw this little axis in, just to show that it's perpendicular. We have Fn over there, and we also have force of friction. You may also get the marks for this question if you had drawn the following that I'm going to show you right now. If you have, just want to make space here. If what you drew looks something like this, where you have your force of friction here, as well as your Fg parallel, you may get marks for it. But I would just recommend having the actual forces and not components here. So for this question, they would have given you the marks for either or, but go with this one over here. Have the actual forces acting and not the components, so you don't confuse yourself. Oh, so there's no opportunity for you to confuse yourself. Cool. Now, let's carry onwards. Let's calculate the total work done on the object by the non-conservative forces when the block is moved from point A to point B. Quickly in the chat, can you tell me what the non-conservative forces are in this scenario? What do we think the non-conservative forces are? Do we know how to identify non-conservative forces? Do we know which forces are typically associated with non-conservative? That would be the force due to friction and our applied force. Cool. Thank you for answering in the chat. Let's go to it. We don't necessarily have to deal with that now, but I was just testing if we do recall. What we should note, I didn't explicitly state this earlier, but the total work or the net work is equals to the work due to our non-conservative forces plus our work due to our conservative forces. For I think matric level, the only conservative force you deal with is potential energy. Maybe they might try throw in a spring. I haven't seen that though. But yeah, your network is the sum of your conservative and your non-conservative forces, where this is your work due to your applied force plus your work due to friction, and then that is your work due to gravity. This is where we get the formula that I showed earlier in the beginning of the session of work net is equals to your work due to applied force plus your work due to friction plus your work due to gravity. This is where we get the formula from. We get it from this right here. I'm not too sure if you guys are familiar with that formula, but let's carry on. Let's get the total work done on the block by the non-conservative forces. This I can find by getting the change in kinetic energy plus the change in potential energy. Cool. I'm then gonna expand these. I'll have half m in brackets Vf squared minus Vi squared plus mg multiplied by delta H, which is just HF minus HI. All right. Now, they tell us in the scenario that the block is initially at rest, so we know that our initial velocity is 0. They also give us the other values, such as the speed, the final speed, or the speed at point B. They also tell us the vertical displacement, which is the height, as well as the mass. So we have everything to solve this. If I substitute in the values, I end up with the following. Half times 12, open bracket, 2,25 squared minus 0 squared, close bracket, plus 12 multiplied by 9,8 multiplied by, in brackets, 4,5 minus 0. I see people are already getting the answers. We have 559,58 joules, which is indeed the correct answer, so well done on that. The work due to non-conservative forces over here is 559,58 joules. If you guys want to revisit this, we do post these videos on our YouTube, so please do check that out. But anyways, let's carry onwards then. That's how we get the answer for this question in particular. 4 marks, 1 mark formula, in this case 2 marks for the substitution, 1 mark for correctly substituting into our kinetic energy part of the equation, another mark for substituting correctly into the potential energy part of the equation, and a final mark of getting the correct answer. Any thoughts on this? Are we good? Are we solid? Can I get a thumbs up? We can hopefully finish off this question then. Right. Now for 5 marks, they ask us to calculate the distance from point A to point B. So they want us to find essentially that over there. They tell us that the constant force F now moves the block at a constant velocity across a rough horizontal surface from points B to C. As shown below, force F acts parallel to the horizontal surface. The magnitude of the constant frictional force acting on the block while moving from point B to point C is 42 newtons larger than the magnitude of the constant frictional force acting on the block when it moves from point A to point B. So now they've given us a way to relate the friction from A to B to the friction from B to C. That's what they have given us over here. And they want us to calculate the distance from point A to point B. So with this one, do you have any ideas on how to approach it? First and foremost, let's get our relations correct. We are told that the constant frictional force, F, from B to C is 42 newtons larger than the constant frictional force acting on points A to B. So I'll keep this as F, but the friction along points A to B, I'm gonna call that F1. So I know now that F minus F1 is equals to 42. Right. Now from here, let's get to actually solving. We have to now bear in mind the value that we found previously. The work due to non-conservative forces is equals to 559,58 joules. So that's important for this question. Let me write that down over here. Just so I don't take up too much of you guys' time, I'm just going to quickly go through this question. So for this one, we start again with our work due to non-conservative forces formula is equals to delta EK plus delta EP. So I change in potential energy plus I change in kinetic energy. This will then allow me, because I did find the work due to non-conservative forces between points A and B, I can substitute in that value. I'll have 559 from a 5.8, and that's going to be equals to oh, hi, sorry about that. My connection cut for a bit. We can finish that question if you guys would like to. We are at the end of the session though. So can I get a thumbs up if you'd like to see the rest of that question, or if you're tired and you think we've done enough for today, all is well, we can continue on and just wait for the next session. So I do see a thumbs up. I am going to share my screen so we can finish that off. Cool. Right. So with this one over here, I'm just going to skim past this question. I'm going to do, so what I'm doing right now is I'm essentially taking the work due to non-conservative forces and I'm finding it for the whole motion in a sense. So I'm taking it from point A up until point B. Are you with me? Let's do so. Oh, wait, I'm taking from point A up until point C, essentially. So what I'm going to have is, let me expand this. I'll have the work due to non-conservative forces. That's going to be equals to our work due to friction with a capital F plus the work due to F1. That's going to be written as such over here. Now from here, in actual fact, let's see. Okay, sorry, my apologies. We're actually doing the work of friction between points A and B. Let me clarify that. So I'm just trying to rush through this question so you guys can at least see how to do this and maybe you guys can reattempt it at home or in your spare time. From here, I can write 559,58. That's going to be equals to F times delta X cos of 0 degrees plus F1 times delta X cos of 180 degrees. Cool. Perhaps I should state it now. Our F in this case is the applied force, or the constant force F acting along A and B. F1 is the friction acting between points A and B. We have the work due to non-conservative forces we computed or calculated in the previous question. From here, I can have it as the following. I'm just going to simplify. F delta X cos of 0 is 1 minus F1 delta X, because cos of 180 is negative 1. I'm taking the motion along this right there. That's going to be equals to 559,58 joules. I'm going to factorize this just to make it a bit easier to work with, and have it as F minus F1 in brackets multiplied by delta X. Cool. Now we're still working along the horizontal. We're told that the magnitude of the constant frictional force acting on the block while moving from B to C is 42 newtons larger than the frictional force acting between points A and B. So if I have the friction here as F1 and perhaps this one as F2, and we told that the force of friction between B and C is 42 newtons larger than that of between A and B, I can have the following. I'll have F minus F2 is equals to MA, right? I'm doing this because I'm essentially finding the net force, basically. We're told that we have a constant velocity between points B and C, and that's going to be very beneficial. I can then have F minus F2 is equals to m times 0 because we have a constant velocity. And that therefore means I have F minus F2 being equals to 0. And we know that F2 is 42 newtons larger than F1. So I have F minus, in brackets, F1 plus F2 is equals to 0. And this simplifies to become F minus F1 is equals to 42. This is how I got this right here. I'm just setting my relations. I'm relating F1 to F2, and then I'm also using the fact that there's a constant velocity between points B and C. And that constant velocity, I can use it to get the net force, whereas the net force acting between points B and C is just the F applied force minus my F2. This right here is F net. Cool. Now from here, since I know that F minus F1 is 42, I can substitute that into the brackets here. I'll have 42 times delta X is equals to 559,58 joules, and then I then have delta X is equals to 13,32 meters. Thank you all for joining. That's just about it. Try to keep it as short as possible, but also I wanted to include the trickier questions. that they may throw at you in exams so that you're fully prepared, or so that you can at least know what's expected of you. Thanks so much for joining. Really appreciate you guys taking time out of your day to join us. We do have the electric circuits session starting at 6. So if you're joining that one, freshen up. Do join if you find this helpful. Please do share to your fellow peers or anybody that you think might find this interesting. Okay, guys, thank you so much. See you guys another time. You can check out these recordings on our social media pages if you'd like to go revisit something or you'd like to share to a friend to see. Otherwise, thanks for joining, guys.